Have you ever looked at a measurement and thought to yourself, what difference does a couple of extra zeros really make? I mean, is 4.700 meters exactly the same as 4.7 meters? Just think about that for a second. Your everyday intuition, and for sure your basic calculator, would probably just scream, well, yes, obviously.
But here is the totally surprising truth. In math, yes, but in physics, absolutely not. When we're measuring the actual physical world, dropping a digit isn't just some minor typo. It is a massive loss of vital information. Because those extra zeros, they communicate the exact precision of our measuring instruments. In the real world, confusing 4.7 with 4.700 could literally be the difference between a perfectly engineered bridge and one that just collapses under its own weight.
Welcome to this explainer. Look, today we aren't just going to be staring at some dry list of textbook rules, okay? We're going to completely decode the universally agreed upon language of science. We'll explore exactly how scientists communicate physical reality with absolute crystal clear clarity, using units, significant figures, and dimensions. You can kind of think of this as your personal masterclass in the vocabulary, the grammar, and the syntax of the entire universe.
Okay, let's dive into this. Here's our roadmap to conquer these concepts step by step. First, the language of measurement. Second, mastering significant figures. Then, calculating with confidence, followed by the power of dimensions, and finally, deducing physical realities.
So, starting off with Section 1, the language of measurement, or as I like to call it, the vocabulary of reality.
Every single measurement requires an internationally accepted reference standard, right? We just call this a unit. And to bring order to a chaotic world, scientists developed the International System of Units, also known as the SI system. And what's really interesting here is that the entire mind-boggling complexity of our physical universe can be broken down into just these 7 fundamental base units. That's it. Whether it's the mass of an entire galaxy measured in kilograms or the time it takes light to zoom across your room measured in seconds, these 7 quantities form the absolute foundation of everything we can possibly measure.
Now you might be wondering, what about things like speed or density or force? Well, those are what we call derived units. Basically, everything else we measure in the universe is simply a mathematical combination built straight out of those magnificent 7 base units. Like velocity, that's just length divided by time. It's seriously such an incredibly elegant system.
Moving on to Section 2, mastering significant figures, which is really the grammar of precision. So if the SI base units are our vocabulary, significant figures act as our grammar. They accurately communicate the exact uncertainty and precision of our instruments. That way, anyone reading our data knows exactly how reliable it truly is. Now, the rules for this can seem a bit tricky at first glance, but I promise they are incredibly logical. First up, all non-zero digits always matter. Zeros sandwiched right between them? Yep, they matter too. But here's where people usually get tripped up. Leading zeros never matter. They're literally just there to locate the decimal point. And trailing zeros, well, the crucial point here is that a trailing zero without a decimal point is completely ambiguous, so it's considered not significant. But if there is a decimal point, those trailing zeros are absolutely significant because you deliberately wrote them to show that exact level of precision. To completely clear up any confusion about those pesky trailing zeros, scientists use a brilliant workaround: scientific notation. Think about it. If you just write down 4,700 millimeters, it's super ambiguous. It might have 2 significant figures, or hey, it might have 4, who knows? But by using scientific notation and writing 4.700 times 10 to the power of 3, you provide perfect clarity. The power of 10 tells us the scale of the measurement, and the base number firmly establishes our level of certainty, telling us we have exactly 4 significant figures. Boom, no ambiguity whatsoever.
All right, let's hit Section 3, calculating with confidence. This is arithmetic with real-world stakes. When you actually take these real-world measurements and start doing math with them, you have to be really, really careful. A final calculated result can never, ever be more magical or more accurate than the raw, messy measurements it originally came from. Let's actually test this out with a quick mental calculation. Imagine you have exactly 12.9 grams of a chemical and you subtract 7.06 grams from it. So, what's the answer? I bet your brain, and definitely your calculator, will probably tell you it's 5.84 grams. But wait, in physics, the answer is exactly 5.8 grams, not 5.84. Why is that? Because when we add or subtract, the absolutely crucial point is we must round our final answer to the least precise decimal place of our inputs, just to reflect reality. Since 12.9 is only precise to the tenths place, our final answer can only be reported to the tenths place. We simply cannot claim a precision of hundreds right out of thin air. It just doesn't work that way.
Now the rule shifts just a little bit for multiplication and division. Here, we care about the total number of significant figures. Let's walk through this real-world density calculation. We're dividing a mass that has 3 significant figures by a volume that only has 2. Naturally, your calculator just spits out 4.7833 and on. But here is where we step in and ruthlessly drop those insignificant digits. Because our least precise raw measurement had only 2 significant figures, our final answer must be rounded to exactly 2 significant figures, so 4.8 grams per cubic centimeter. Doing this maintains strict scientific integrity.
Which brings us to Section 4, the power of dimensions, the underlying syntax of reality.
So, if units are our vocabulary and sig figs are our grammar, dimensions, well, they are the underlying syntax of reality. We represent the fundamental raw nature of these quantities using brackets, so like m for mass, L for length, and T for time. It completely strips away the specific numbers and units to just reveal the true physical nature of whatever we're looking at. And this introduces a massive golden rule in physics, the principle of homogeneity. It states that you can only equate, add, or subtract physical quantities if they have the exact same dimensions. It's basically the high-level scientific version of saying you can't add apples and oranges. Or, more accurately, you simply cannot add velocity and force.
Let's actually use this principle to solve a classic physics puzzle. Take a look at the famous formula for kinetic energy. K equals 1/2 mass times velocity squared. Now, is this equation actually dimensionally sound? Well, let's put it to the test.
Let's move to this and see exactly how it builds. We're going to put on our dimensional detective hats here. Step 1, the left side. Kinetic energy has the dimensions of mass times length squared divided by time squared. Okay, step 2, the right side. We take mass, which is just m, and multiply it by velocity squared. Well, velocity is length over time, so we just square that whole thing to get length squared over time squared. Now we multiply them together, and look at that! The right-hand side perfectly matches the left-hand side. The equation is perfectly balanced and physically possible. And by the way, notice how we totally ignored that 1/2? Yeah, that's because pure numbers don't have dimensions at all.
And finally, Section 5, deducing physical realities, finding the formula.
Okay, get ready for the ultimate cheat code of dimensional analysis. Because the universe simply must balance dimensionally, we can actually use this method to deduce brand new relationships and formulas completely from scratch, just by knowing what variables are involved. Imagine a swinging pendulum. Let's say we suspect the time it takes for one full swing, the time period, somehow mathematically relates to the length of the string and the acceleration of gravity. So we just organize our known variables and their fundamental dimensions. Length is L, gravity is Lt to the -2, and time period is T. By strictly forcing the dimensions on both sides of a hypothetical equation to balance out, the math automatically reveals how the variables must relate to one another. We deduce that time is proportional to the square root of length divided by gravity. Seriously, it's almost like magic. Now, to be totally honest, there is one limitation to this incredibly powerful method. Dimensional analysis cannot magically find pure dimensionless constants, which we represent here with the letter K. For that missing piece, we'd have to actually run a physical experiment. But getting the core formula just from the bare dimensions of reality, that is absolutely mind-blowing.
So, let's bring this all together and wrap it up. We have just explored the 3 fundamental pillars, the cheat codes, of physics. First, the SI base units form our essential vocabulary, empowering us to describe literally everything in reality. Second, significant figures provide a strict, unyielding grammar of precision, ensuring we never overstate the accuracy of our raw measurements. Because hey, we don't want any bridges collapsing. And third, dimensional analysis acts as the undeniable syntax of reality, serving as a foolproof check on our equations and even allowing us to discover brand new physical laws.
Which leaves us with one final, fascinating thought. All the chaos, all the immense complexity of the physical world you see around you, every single galaxy, every molecule, every invisible force, can literally be reduced to just 7 fundamental base dimensions. It really makes you wonder, if all physical reality can be reduced to just 7 base dimensions, with a toolset this incredibly elegant and precise, what else in the whole universe are we just waiting to measure? Thank you so much for exploring this explainer with me today. Keep asking questions and keep analyzing the world around you.